Everyone, good morning. Welcome. Thank you for coming. I'll share my screen and then we'll get started. Okay, everything looks like it's up and running. And here we go. This is our schedule for the next 3 days. We'll take 15-minute breaks at 11:15 in the morning session and at 2:30 for the afternoon session. Before each of the sessions end, morning and afternoon, I'll stop a little bit early and take any questions that you have. The Slack application bulletin board is another possibility for posting questions. And if there's a question that's more individual or would require a more detailed response, then I think I would ask you to post that on Slack, and I'll follow up with an answer. There's a list of references at the end of each set of slides. And there are a total of 2 assignments for the seminar, one that I'll describe in just a few minutes, one that I'll describe tomorrow, and both of these assignments are described on Slack in terms of the goals and a little bit more detail about what they are. Okay. Without further delay, let's get right into things. I really like Judea Pearl's definition of structural equation modeling as a causal inference method with 3 basic inputs and 3 basic outputs. The inputs are hypotheses about causal effects among variables of interest. Those variables could be measured or hypothetical or latent. And ultimately, your causal hypotheses are represented in the form of your model, which could be expressed in graphical form, or when the computer analyzes the model, it ultimately expresses your model as a series of equations that it simultaneously solves with your data. Along with basic causal hypotheses, there may also be interested in queries or questions, including things like the magnitude and signs, positive or negative, of presumed causal effects. And the third input is eventually, of course, your data. Now, in just a few moments, I'm going to describe one aspect of structural equation modeling where you can analyze your causal model to make sure that you can estimate the basic effects represented in that model with no data. That is, it's possible to, if you will, evaluate your hypotheses before you ever collect any data, which in statistical modeling is not a bad idea. Because if there's a problem with your model, before you got data, this gives you a chance to try to fix those issues. The basic outputs from structural equation modeling are the parameter estimates for various effects represented in your model. Causal, they could be direct, indirect, or also just associational. There are also, typically in most SEM analyses, testable implications for fitting the model to the data, of which probably the type that's reported most widely, yet typically incompletely, concerns model fit. Now, there are 2 aspects of model fit, global and local. Global refers to the overall or average correspondence of your model to the data, and local fit concerns how well your model explains the observed associations between every pair of measured variables that's represented in the model. Local fit is much more molecular, much more detailed than global fit. And a point that I'm going to emphasize time and again, you may get tired of hearing me say this, but complete reporting about model fit in SEM requires commentary or reports about global fit or overall fit plus local fit, which are the details of fit. A common shortcoming in many, perhaps most, published SEM studies is that researchers almost always describe global fit, but unfortunately, relatively few describe local fit. So I'm going to emphasize for all of our examples and all of our discussion that you comport completely, accurately, and transparently about model fit at both levels, global and local. I have represented here the 6 basic steps in structural equation modeling. In the next slide, I'll define steps 2 through 6, or identification through reporting. Also, in the next slide, I'll show that going through these 6 steps is typically iterative, which means that you may reach a certain point in these steps where it's necessary to return to an earlier point in the process and, if you will, try again. And then it'll eventually wind up with the reporting phase. But what I'm emphasizing here is that the very first step in an SEM analysis is the specification phase. And the specification phase is more important than all the rest, maybe even combined, because in the specification phase is where you represent your basic hypotheses. That is, you specify, you create, you construct your causal model. And thinking about that expression from computer science, garbage in, garbage out, if at the first step in SEM, your hypotheses are problematic, then everything else throughout the rest of the process will reflect those initial problems. Also, at this point, I want to try to empower your sense of being a researcher rather than being a statistician, which I assume that most of you are not. I'm not a statistician, as the introduction suggested. Instead, I came to SEM because this family of techniques represented ways to address various types of questions or hypotheses that we had. So the most important thing that you can bring to your own work in SEM is your knowledge as a researcher, is your domain knowledge as a researcher. That is, knowledge of theory, knowledge of operationalization, knowledge of measurement, and knowledge of what makes for interesting hypotheses in their area. If you can do that, then the rest of the steps will fall into place. But step number 1 is the very most important. Shown here is a flow chart showing the iterative nature of the various steps in SEM. Step number 2 concerns identification, where identification means that it's theoretically, mathematically possible for the computer to, once you fit the model to the data, for the computer to come up with a unique estimate for every effect that's represented in your model. If that is not possible, then the model is not identified, and models that are not identified are not amenable to statistical analysis without some very special kinds of intervention that we're not going to get into in an introductory level workshop. So step number 2 is, after you specify the model and represent it as typically as a model diagram at this point, to ask the question, is the model identified? If it is not, you have to go back and fix something about your model. And this can be done and should be done before you have any data whatsoever. And the capability to analyze your model with a computer tool to inform you very specifically about whether each and every effect in the model is identified, is analyzable, that capability I'll say some more about in just a few moments. Step 3 is collect, prepare, clean, and screen the data. Step 4 is where we come down to the analysis phase. And this is where the model is eventually fitted to the data matrix in your sample. Now, probably most of the time in SEM studies, the fit of your initial model to the data will be judged as not adequate. So the answer here for is model fit adequate is typically no. So that would bring you to another decision point, which concerns, is there a theoretically justifiable way to re-specify the model that may improve model fit? Justified in theory, justified in empirical research in the area. If there is, if the answer is yes, then you re-specify the model and you try it again. You fit it to the data again. Now, there are two different branches here. Let's assume that at this point, after re-specification, model fit to the data is adequate, both in terms of global and local fit. So what would proceed from there would be to report and interpret the parameter estimates. Here, I'm assuming that information about model fit, global and local, would also be reported. Down at step 4C, that you consider the problem of equivalent or near equivalent models. We'll talk about this issue tomorrow. And then the last step would be report the results. Now, let me come back up here to step 4A concerning is model fit inadequate? Let's say the answer is no. Maybe you've gone through a round or two of specification. Things still don't look great. The answer here is still no. But at this decision point, let's say that you're out of ideas. You're out of theoretically justifiable re-specifications for the model. Here, I think it would be better to say no, to proceed directly to reporting the results without retaining a model. And it is a perfectly acceptable outcome in SEM to retain no model in the analysis. So that would bring you directly down to the reporting stage. Now, this point here, and this is why I have this emphasized with the red bracket, that it's acceptable, or rather, let me put it like this. There is no requirement to report on, to find, discover a model that is consistent with the data. And retaining no model is a perfectly acceptable outcome. This is because, and now to talk about two very bottom lines in the analysis, probably I think the most important principle of structural equation modeling is to keep your eyes on the prize. And the prize in SEM is testing a theory. The prize is not retaining a model. This is because any model that's identified, any model, even one that is grossly wrong, that you know is grossly wrong, can be made to fit any data set with basically the same variables, simply by making the model more complicated, adding effects to the model. And when you make a model more complicated, it will eventually fit the data, because it becomes basically as complicated as the model becomes as complicated as the data the model is supposed to explain. So in structural equation modeling, retaining a model by itself is not very impressive. Anyone can do that at any time, even with a randomly specified model made sufficiently complicated, will perfectly fit not only your sample data, but data from any other sample for the same variables drawn from the same population. Another way to describe this situation is when models have 0 degrees of freedom, and I'll explain what model degrees of freedom are, how they're counted, how they're defined in more detail tomorrow. But models with 0 degrees of freedom are as complex as the data matrix to which the model is fitted, and such models must perfectly fit the data. So the whole trick is to retain a model that's not as complex as possible. So it still has the possibility to disagree with the data and is theoretically justifiable. If it's not theoretically justifiable, then perhaps all you're doing is capitalizing on sample-specific variation, and the model will fit the data, but it probably will not replicate. So the bottom line priority here is to test the theory and in reporting be as complete as possible. This quote from Carl Bernstein speaks to, I think, what is an ideal in scientific reporting for any kind of research, including for the types of research that we do, also in structural equation modeling. Unfortunately, the state of reporting in the SEM literature for published empirical studies is, let me put it graciously, is poor. There's need for improvement. To speak more directly, the state of reporting, I think, is in a state of crisis, such that many, I don't want to overspeak and say most, but I think many published studies fail to give readers enough information so that the readers can understand whether the model is really consistent with the data, such as the state of reporting in SEM. And if readers aren't told all the details about model fit, they're also not reassured about whether any of the interpretations that you've worked very hard to refine in terms of writing the manuscript, whether any of those interpretations have any substantive value. Now, we know that the state of reporting for SEM empirical studies is rather poor because there have been several, I can think of at least a dozen works of this type. There probably are many more. There have been many publications in various disciplines where researchers take a look at published SEM studies, typically for a particular time range, maybe in a particular research area, in particular journals. They read those articles and they evaluate them for the completeness, the clarity, and the transparency in reporting. And across most of those studies, the conclusion has often been, well, there are some interesting applications here, and SEM is applied to some fascinating kinds of hypotheses, but reporting is really incomplete, and it's a big problem. Here's an example of a review. It's one of our works in the area of organizational and management research. I'll briefly describe some of our findings in a review of 144 articles where SEM was applied in this research area, in a total of 3 different journals in the area, just to give you some sense of the kinds of problems in reporting that have also been found by many others. So what we had to say here about the state of reporting in this area is not unique. Also, coming up, the next 2 slides, I'm going to show you a graphic that is really busy It's kind of a poor slide for a PowerPoint presentation, but I do have marked in each of those the particular points that I want to emphasize. So here's the first overly busy slide. And here I want to highlight some things that authors of these nearly 150 studies did well, where they did where the reporting was nice and clear. For example, looking at the top of the bar chart, the hypotheses, the basic hypotheses, were just clearly described in most studies. Somewhat less strong was looking at the very first point. Only about 40% gave an explicit justification as to why SEM would be an appropriate type of analysis. Things would be more complete if they did that. Looking down at about the middle of the bar graph for reliability, nearly all of the studies reported something about the psychometrics of the measures that they were using. And I think this 99% is really very admirable. So that's a plus. Looking at the lower third of the diagram, most of these areas concern global fit. The very last one concerns local fit. I'll mention that on the next slide. But most researchers were pretty good about reporting some, but not all aspects of global fit. For example, it was very common for researchers to report fit indexes that we'll talk about tomorrow that include the CFI, or the comparative fit index, also the model chi-square, which is a significance test. We'll talk about that tomorrow as well. They weren't as complete in reporting about a statistic called the RMSEA, mainly because they did not report its confidence interval, where the upper bound of that interval will be typically less favorable concerning global fit than the overall point estimate for the RMSEA. So some aspects of reporting over the sets of studies were really pretty good, were really pretty strong. But there are other areas that weren't so good, looking at the top part of the display. Most authors gave little, if any, justification for their sample size. Now, this is an issue we'll talk about as well. And in other kinds of statistical analyses, using power analysis is one way to give a rationale for example, why is your sample size 375 versus some other value higher or lower? It's possible to do that in SEM, including in situations where you're writing a grant request and some granting agencies require explicit justification for sample size. And it's possible to do that in SEM. We'll talk about that coming up tomorrow. I mentioned earlier that some aspects of reporting about global fit concerning the RMSEA statistic is relatively incomplete. Only 7% of authors gave complete information here. And going down to the very last point at the bottom of the screen, about 17% gave information about local fit. Now, compared with other studies where they reviewed empirical SEM studies, that 17% figure is impressively high. Ideally, it should be 100%. I was pleasantly surprised to see it as high as 17% in this set of studies. But this is an area where, but I've seen other reviews where maybe no single study mentioned something about local fit, or maybe just some minimal information was reported. And I've seen some rates where it's maybe 2%, 3%, 17% is on the high side, but reporting only about global fit is not sufficient in SEM. Now, how to report completely about global and local fit, we'll get into the details of that tomorrow. And in fact, our discussion all day tomorrow is about how to evaluate model fit. As Matt mentioned earlier, I had the privilege of being a part of the group, being part of the working group that helped to revise the journal article reporting standards for quantitative studies for articles published in APA journals. In this revision of the APA reporting standards, we incorporated into the standards a set of SEM reporting standards published originally, I believe it was 2013, by Rick Hoyle and Jennifer Isherwood for the journal Archives of Scientific Psychology. That was for its time, a very complete set of standards. The authors did emphasize strongly, and this is one of the reasons that drew our attention to it, the need to report in a comprehensive and transparent way about model fit. And what we did in the working group was we adapted their standards for inclusion in the APA reporting standards. We modernized some of the language. We changed some of the wording to make the SEM standards more consistent with reporting standards for other types of empirical studies, other types of quantitative studies. And for the first time, the APA standards include explicit reporting standards, or what should be reported for SEM analyses. Now, this article is available to you in the course materials. What I suggest you do with it is, I think you can skim it. You're an experienced audience. I think you know the basic issues of reporting and the need to do so in a complete way. But if you would skim this article up to the description of Table 6, which is where the SEM reporting standards are described, and that table is roughly about a page and a half long. Now, here's another work that's also available in the course materials. And this is where I'm putting my money where my mouth is. That is, this is a way of me saying, I'm not just a critic who has no involvement in practice. I try to, in my own work, as best as possible, respect reporting standards in a particular area that I'm working in. So here I'm offering up this article, and this also concerns our first assignment, where what I would like for you to do is read this article with focus on what was reported, what we reported in this article, and compare that to the APA SEM reporting standards. I think you'll find in this article, and this is one of the reasons why I'm offering it up as an example, that we did give, I think, complete information about model fit, global and local. We also made all computer output available, all syntax files available, and the data are also available as supplementary materials. So I think this is an example of complete reporting about model fit. Also, and this is the other reason I'm having you read it, it's not perfect. That is, that there are things that we could have done better in terms of the reporting here concerning the APA standards. So what I would like for you to do is read this article and just maybe keep track of what are the things that we did well concerning APA reporting standards, and what are some areas where we should have provided more information. So when we start things off on Saturday, we'll talk about this article. I'll get your impressions, And I'll give you at least my summary of what I think we did right versus the ways in which we fell short of meeting everything in the reporting standards. Okay. I'm going to take a quick look at chat questions. And, okay. Right, and I do see a question from OG about how many indicators should there be per factor for a measurement model. We'll talk about that on Saturday. And also coming up later in today, I'll describe in more detail the 3 different types of models that we're going to talk about, the 3 examples from actual studies that we'll take a look at in great detail over the next 3 days. So OG I'll be coming to your question on Saturday. Okay. Another work that's in the materials for the class is this recently published, I believe this is, and I don't see the year here directly, I think this is 2021 or 2022. This is a set of reporting standards for those doing mediation analyses in either randomized clinical trials, where there's some type of experimental variable that involves random assignment to, at minimum, treatment versus control, or also in observational studies. There's a fair amount of overlap between these standards by Lee and many others, and those for general SEM reporting in the APA standards. There is more specific focus here on mediation per se. Now, starting tomorrow, well, starting a little bit today, and in more detail tomorrow, we'll talk about topics that include mediation analysis, indirect causal effects, estimation of mediation and indirect causal effects, design issues, and interpretation issues. So the analysis of indirect effects, of mediated effects, is of interest in many published SEM studies. There are also many challenges in doing mediation analysis that the researcher should address in both the analysis and the reporting phase. And we'll be talking about those issues again a little bit today, but continuing over the next couple of days. And here I have a question from Vikas. We'll be talking about model overfitting and generalizing results outside the sample. Yes, we will be, and I already mentioned that just implicitly, but I'll just make a quick point now. The more complex your model is, the fewer degrees of freedom that it has, the more you are probably overfitting, which means that you're capitalizing on sample-specific variation. You're capitalizing heavily on sampling error in a particular sample, such that the model probably will not generalize to other samples drawn from the same population. Another general principle here that we'll talk about more on Saturday. The more that you rely on statistical significance testing in the re-specification phase in step number 5, or going from that circle from steps 4 through 5. The more you rely on significance testing to re-specify your model, probably the more you are overfitting and capitalizing on chance variation. It is much better to be guided by hypotheses, rationale, results from prior empirical studies, than trying to apply significant study to somehow find a model that's consistent with the data. You're guaranteed to find such a model, as I suggested earlier, but would it replicate? Well, probably not. So another underlying theme for our time together the next 3 days is, in addition to reporting about both aspects or levels of fit, emphasizing your ideas, emphasizing your hypotheses. And if doing so means that you don't retain a model, well, then so be it. And sometimes retaining no model can be a more interesting finding than retaining no model. But these ideas and themes we'll be talking about coming up. Okay, so these are 2 articles that you have available to. All right. What I'd like to do next is describe the 3 families of techniques that make up structural equation modeling. That is, SEM is not a single set of techniques. Is not a single family of methods. There are actually 3 different areas that over the last 60, 70 years or so have been developed relatively separately in different disciplines. But I see these 3 families as finally coming together, as converging. And knowing something about SEM, I think ideally means that even if you're working mainly in one of these 3 areas, that you know something at least about what some of the other areas have to offer. Now, again, to describe context here, we're going to spend most of our time talking about covariance-based structural equation modeling, which is the SEM family that's probably most familiar in disciplines like psychology, education, and sociology. It's also the kind of SEM that one sees applied most often in the literature, although that has been changing as there have been more and more studies coming out of the other 2 frameworks. There will be times, even after today, where I will come back to both the other families besides covariance-based SEM. But most of our time will be spent talking about families in these areas. Variance-based SEM, and there are some alternative names that I'll give coming up, was developed, is more well known in areas like commerce, management, economics, where researchers often analyze indexes or composites or weighted combinations of observed variables that estimate some hypothetical or theoretical entity. So if you're from a background in one of these areas, you're probably more familiar with variance-based SEM. Non-parametric structural equation modeling would be more familiar to those, especially if you work in epidemiology and or medicine. Although parametric SEM is becoming more widely known in additional areas. Non-parametric SEM has some pretty unique features that can offer that are available to those, I think, especially for those who work in the covariance-based family. But next, what I want to do is define each of these areas in enough detail so at least we have some context. And so we can talk about how CB-SEM differs from VB-SEM versus non-parametric. All 3 of these families have the same origin, and that origin is work by the geneticist Sewall Wright, who developed the technique of path analysis over a series of publications in the 1920s and the 1930s, and continuing up through about the mid-1960s. Very quickly described, Sewall Wright described a technique where, given a causal model, how does one go about estimating the directions and magnitudes of causal effects represented in that model from observational data, from correlational data, where you have from a sample information about the magnitudes and directions of correlations, covariances among variables of interest. How do you take what's basically a correlation or a covariance matrix and decompose it to extract estimates of direct or possibly indirect causal effects? So the origins of SEM lie with work in genetics about the question that I just described. Now, this article, which is from 1920, later, and I don't see the page number in the article, but figure 5 is in this 1920 article. And this is, I believe, the very first path diagram, the very first structural equation model that appeared in the research literature. The model looks a lot like, especially path models today, or structural equation models in general. In fact, it looks a lot more fun with these icons for the predictor and outcome variables. But very quickly, what we have described here is, this is a model of causation about coat patterns, coloring in offspring, in baby guinea pigs, given information about the coat patterns for the sire and the dam, for the mother and the father, and other variables. So this is a model that represents both measured variables, like coat pattern in the babies, coat patterns in the parents, and it also represents latent variables or causes that are not directly measured. So included in the model are both measured and hypothetical or theoretical causal variables that aren't measured directly with things like guinea pig coat patterns, but have to be inferred in the analysis through some of the observed variables, also called indicators. Also represented in this model in the left-hand side, about over here, would be random error, would be the error terms for these various effects. So this model represents both presumed, direct, and indirect causal effects. It also represents predictions of, and we'll talk about this coming up, predictions that some of these variables could be related due to reasons that have nothing to do with causal effects. Instead, their associations are just that. They're just covariances. They're just due to spurious effects, or they're associational. So here is again, the very first path diagram, which looks very similar to what we work with today. Okay. Covariance-based structural equation modeling represents the synthesis of two areas of statistical analysis. One would be classical regression techniques for observed variables. This would include things like multiple regression for continuous outcomes, logistic regression or probit regression when outcomes are categorical, ordinal regression when outcomes are ordinal, not quite continuous. So regression here represents the whole set of regression techniques for observed variables only. And in classical regression techniques, there's really no convenient way to represent latent variables or hypothetical constructs that are measured approximately with observed variables. So the other half of covariance-based structural equation modeling represents factor analysis, and more specifically, common factor analysis. That's been described since roughly 1904, 1905, first by Charles Spearman, and then continuing through since that time. And here I'm thinking about factor analytic techniques where variables are combined and their common variance, their shared variance, is used to estimate presumed underlying factors. And those underlying factors are represented as, in part, causes of scores on the observed variables or the indicators. Also, classical methods of common factor analysis estimate the degree of measurement error associated with each individual observed variable. So here I'm not thinking about the principal components method of factor analysis. That's a method for composites that would belong to or be related to the variance-based SEM family. Here I'm thinking about more classical factor analytic techniques to test hypotheses about theoretical variables that are not directly observed. So the original uses of factor analysis were to test theories about the nature of human intelligence, but that since has expanded to many other applications. Putting these two families together, what one can do in covariance structural equation modeling is, if there is some hypothesis that, let's say, you have a set of variables that you think measure some common area, some common factor, those variables can be represented as the indicators of what I'm representing here with an L, or a latent variable. And those latent variables are estimated with common factors. And common factors are defined by the indicators that should go along that particular factor. Also, in classical factor analysis, as I mentioned, measurement error is taken into account, is controlled for in the analysis, and that's also a feature of structural equation modeling in the CB-SEM area. Now, classical regression techniques don't have a direct way to control for measurement error, but that is certainly possible in covariance-based SEM. There is a question in chat from OG about latent regression. That's a form of structural equation modeling. That's a form of CB-SEM, where either predictors or outcome variables could be factors, each of which is measured with two or more indicators or observed variables, while controlling for measurement error in those observed variables. The types of models where that feature would be true, or if you will, latent variable regression, those are called structural regression models. And we have an example of a structural regression model coming up that we'll deal with also on Friday. And to finish up the question, in SEM, latent variables can be represented as either predictors, or if you will, strictly causal, or as outcome variables or as dependent variables. So with covariance-based SEM, there's really a lot of flexibility in the analysis, and it combines all the basic features of regression and classical methods for factor analysis. The term covariance-based comes from the following. And here I'm looking at my first expression here, where the uppercase S in boldface represents the data matrix. the data matrix, which would be, for example, let's say you've got, for all of your measured variables, they're all continuous. They're all continuous. You have a raw data file for those variables. That raw data can be summarized with a covariance matrix for those measured variables, where that's going to include information about the Pearson correlations among those variables, and also their standard deviations or their raw score metrics. So a raw data file for a set of observed variables that's continuous can be completely summarized in terms of its covariance information by converting that raw data file to a covariance matrix, here capital S. The other symbol in my first bullet here, S hat, is the predicted or model implied covariance matrix, which is, given your model and the parameter estimates, the computer can generate, it may be an option, but basically all SEM computer tools can do this. The computer can generate a matrix of predicted covariances, where in that matrix will be the predicted association between every pair of measured variables given your model and given the parameter estimates for the model after that model has been fitted to the data. And for every pair of measured variables, there'll be an observed or sample association versus, given your model, a predicted association. And local fit concerns how well does the model explain the associations for each and every pair of measured variables. Global fit concerns the closeness between the overall data matrix, uppercase S, and the predicted matrix of covariances for the same variables given your model. And the term covariance-based means that computer tools in this area will attempt to minimize the discrepancy or minimize the difference between sample and model, between data and model, or to, if you will, maximize the fit of the model with its predicted covariance matrix to your sample data matrix. Again, given the model and the parameter estimates. So this is the whole goal of covariance-based structural equation modeling, to maximize fit, both at a global level and also an attempt to do so for each pair of measured variables. The first software tool that was widely available to researchers for doing covariance-based SEM was the mainframe version of LIST Rule 3, published in 1976 by, and here pronunciations vary, here's mine, Joriskog and Sorbum. So LIST Rule 3 in the mid-1970s was the origins in terms of a software tool, was the progenitor of all computer software for SEM. So later programs like EQS, M+, AMOS, etc., all have their roots in LIST Rule. And of course, LIST Rule is still available as well. But the overall goal in covariance-based SEM is to minimize the discrepancy represented in this quantity. Also, in covariance-based SEM, and this is coming from its origins in factor analysis and common factor analysis, which was developed originally to test theories about the nature and organization of human intelligence. There's a strong emphasis on theory testing, also on explanation in the form of your model. That is, your model should represent your hypotheses about how do variables relate to one another? What, if any, causal effects do they have between any pair of measured variables in the model? What are all the different ways that two variables could be associated with one another, causal or non-causal? There's also a relatively heavier emphasis on covariance-based SEM, on a priori hypotheses over and a priori oriented analyses over more purely exploratory analyses. And just a quick example to illustrate this difference. We'll talk a little bit on Friday about the difference between confirmatory factor analysis, which is the CB-SEM method of doing factor analysis. CFA is a priori, in that the researcher has to specify many things before the analysis can even get started, including things like, well, you're doing the analysis presumably because you assume there are underlying factors, underlying latent variables. Well, how many? 1, 2, 3? You have to specify the particular number. You also have to specify in CFA which of your measured variables or indicators is associated with which of those factors. That is the indicator factor correspondence. For example, here's a measured variable here. Let's call it x1. On which factor does this measured variable primarily depend? Which of the, let's say, 3 hypothesized factors? And does this indicator depend or measure any additional factors? That is, should it have in the model loadings on a single factor or on multiple factors? Are the error variances assumed to be independent for the observed variables, or are they dependent? Are they correlated to some degree? Well, if so, you have to specify that as well. So in CFA, there's a lot of detail that the researcher has to bring to the table to even get the analysis started. In contrast, exploratory factor analysis, or EFA, which is not in the CB-SEM family, was developed for situations where theory is not as well developed, including situations where there may be little, if any, theory about measurement at all. Exploratory factor analysis, hence the name, is much more oriented in situations where theory is weak, and there's very little that the researcher needs to specify, including things like, how many underlying factors do you think there are? 2, 3, 4? There's no need to specify that. Because typically in EFA, it will generate, unless you restrict it otherwise, every possible factor solution. 1 factor, 2 factor, 3 factors, up until there are as many factors as there are indicators, and it can't go beyond that because the model would not be identified. But in EFA, really all you need to specify is what are the observed variables? You have to pick estimation methods. You have to pick something about rotation options. If you don't, the computer rely on its defaults. But EFA is much more exploratory. Now, we'll talk about this in more detail tomorrow. CB-SEM is not strictly a priori. It's not strictly a priori. There is an exploratory aspect to it, but you need to be careful not to drift too far into the exploratory end. One way to do that, I mentioned earlier, was to rely excessively on significance testing to specify your model, because the more exploratory is the CB-SEM analysis, the more you might be overfitting or capitalizing on sample-specific variation.